look at a queue. So we've got these queues that are being fed or populated by an interrupt service routine, and which are being consumed by a program that is not a interrupt service routine. Same thing with the send. The send is generating these characters, and it will fill, typically at one time, fill the entire queue, and then the transmit ISR will just peel off one at a time. But there might be a situation where we're continuing to send stuff so fast that we need to keep track of both the head of the queue and the tail of the queue. So we're going to have the head of the queue point to the oldest data, and the tail point to the newest data. So in this case, if we have a queue, would the RX be filling stuff or be putting stuff at the tail or at the head of the queue? All right, so the RX is actually taking and putting data at the tail. The get string would then be taking data from the head because it is consuming. Then if you look at the other way, specifically this queue over here, the transmit ISR will be grabbing stuff from what part of the queue? The head, because it's consuming it, and then the send string is actually putting stuff where? At the tail at the end. So that means that you have, oh, by the way, this is also a circular queue too, because as you can imagine, as the head goes down this way and the tail is increasing as well, there will be a point where it reaches the end. And so what does it do? Well, it just wraps around and starts to add stuff up here. And so when does it stop adding stuff? You know, when the head and the tail point to the same place, meaning that there's no room left. There's another way to tell too, and that is when the size is the same as, you know, the size that you think your queue is the maximum queue size that you define for your system. All right. By the way, it's good to use this pound define to create your queue size, because otherwise you're going to be changing variables all throughout. That's another reason why you like magic numbers like this. All you have to do is change it in one place, and all the code is correct. So let's take a look at defining the queue. By the way, in the next class, I'm actually going to hand everybody a sheet of paper that has all of this code, because then you're going to be using this code in the next class, and we're going to identify how to actually run this, because we're going to be using this for a future lab. I actually had several students say, "Oh yeah, and I've used this same mechanism in industry." So it works pretty well. We're going to identify a queue that has data associated with this queue. It's going to be character data. It has a head, a tail, and a size. And interesting enough, our transmission queue is going to be the same construction as our receive queue. Well, that's kind of natural, right? Because if you look at this, it kind of looks like it's the same. They both have a head and tail. They're both going to have a size. So we're going to use it in that same way. Again, head points to the oldest data. Tail points to the next free space. So if you look at this, notice the tail is pointing to free space. That means if tail is then pointing to this use space, it's obvious that it's full. So just like anything else in what we do, it's really good that you can debug code. For example, we're going to set up our queue such that we're going to zero out everything, all right? All the data is going to be zero inside of the queue in both of them, right? The head's going to be zero, the tail's going to point to zero, the size is going to be zero. But we also have identified, oh, and you could do this for, you could feed this in for that receive queue and that transmit queue. Oops. And we're going to have a little function that will actually return 0 or 1. So the queue is empty if the size is 0. And so if the size, meaning the size of the queue that you're interrogating, is equal to 0, then you return a 1. That's important to know because, we're going from 0 to 1, right? We're just looking at the logical. So just consider this true if it returns and is empty. The same with here. Even though the size may be, what did we say earlier here? 32, right? If the size 32 of what we set up is equal to the size and the structure we created, then we're going to return true. Remember, in the world of C code, this equal is equivalent to a logical assessment. So it's going to return either a 0 or a 1. Wow, look at everything it does. One thing I want to point out is that this code here, which is going to enqueue or put on the queue, is going to check to see if it's full. If it is not full, put something on the queue. Otherwise, return 0, failure. In the same way, if you're going to pull something off the queue, if the queue is not empty, why do I always have to pay for donuts? So if the queue is not empty, that means there's something there I could consume. So if there's something there I'm going to consume, I'll pull it off, and then I return the actual character. The interesting thing enough is, note we set t equal to 0. So if you return 0, then whoever is consuming or taking this character needs to understand that it's probably not a real character. And we're going to look at this in more detail in our next class. Thank you very much. All right, we are back. And for those of you who are watching this on tape, make sure to enjoy your favorite beverage. This is not whiskey. That is tea, all right? So we were talking before about using a queue and putting something on the queue and taking it off of the queue. And so I'm going to go through a couple of examples and show you how this works. Whoa. So let's take a look at, this thing just popped off my pocket. So let's take a look at this one in more detail. Remember our structure, and this is important to remember that our structure is identified to have a head, a tail, and a particular size of the queue. And by the way, the transmit and receive queues are the same structure. And if you remember correctly, we would have a situation where we have a UART hardware device, which is going to be, which you're going to work with a set of hardware or a set of software. One of those software pieces being interrupt service routines, one for receive, one for transmit, and then you will consume these characters that are sent to the computer that you're working with and that you want to send back out. So again, the structure has a head, a tail, size, and of course the data itself. And in fact, let me go ahead and make a visual representation of these. So I will have, and just for grins, I'm only going to show 8. So this will be the data, head, tail, size. Now one thing I do want to point out is in the code itself, is this head and tail and size a pointer? No. So you notice that what we're going to be doing is working with specifically an array and the individual or the specific index inside of that array, keeping in mind that somewhere along the line you're going to have to wrap around the end. So we may have, for example, and I'm just going to put a semicolon there. This is where I wish I had the code on one place and everything else on another, so bear with me for a bit. So here we have, I may have to draw this up on the screen. Our data, head, tail, and what's the very first thing we do? And I showed the code for that. We zeroed everything out, right? Tail is 0, head is 0, size is 0. And that all makes sense, right? So let's look back at the code. Remember the empty and the full. So if we want to put something on the queue, look what we do in each one of these steps. Number 1, I might have to just draw all this on the screen. Now let's see. If it is not full, in other words, if we want to put something on the queue, what do? Well, we put something in the data. Now notice here that we say tail plus plus, meaning that what? We're going to use the current setting for tail. We're putting it at the end of the queue, right? And then we're going to post increment the variable tail. And oh, by the way, that's assigned the character that you just read in. So this might be called by an interrupt service routine. The next we do is that we check the value of tail and basically take the modula of it versus queue size. Because if it is the same as queue size, then you want to go to the header of the you want to go to the very first entry. Remember, what does that say, modula? It returns the remainder. So notice that you've done tail plus plus. You've incremented it here. So if you are pointing to the very last entry in the queue, which is element number 7, right? You put something into element number 7. Remember, I'm using 8 at this point. All right, and and then you increment. So now it's 8. The size is 8. So 8 modula 8 is 0. So tail will point to the beginning. You increment the size, and then you return. Notice that you don't do anything here that says that sets any variable or any flag to say it's now full. Because you really don't have to worry about that until you want to add the next character. Take a look at here. You're going to dequeue, in other words, pull off of the queue. You're going to start by assigning the character value as 0. And if the queue is not empty, because this could be called and there might be nothing in it. So what do you do if there's nothing in it? You just return 0. And whoever called it hopefully will say, don't do anything. So here we go. We take whatever the head is. So whatever character is in the data array that the head is pointing to, and we'll put it in T. That's what we return. You increment the head. And oh, by the way, we also we zero it out because there's no longer any data in there that we want. Also, you might be all the way at the end of that array, and so you'll use this modula to wrap back around. And of course, you need to decrement the size. Enqueuing, you incremented. Dequeuing, you decremented. Looks pretty easy, right? Oh, wow. So that's it for that. All right, so if you understand how this works, I'm going to go through a little hands-on exercise that you may never know. It may show up as a quiz. So let's say our instructions will be to the following. We're going to enqueue the data 70. We're going to enqueue the data 64. We're going to enqueue the data 41. We're going to enqueue the data 42. Enqueue the data 43. We're going to dequeue the data. Yeah, did I say that right? All right, dequeue the next data. All right, so let's take a look at how this would operate. Enqueue says, if we look at the code, you could remember it from what I just showed you. Now let's take a look at it really quick so we can just remember everything. So remember, it is check to make sure the queue is not full, put it at the tail, increment the tail, check on the size, or check to make sure that you've not gone past the end of the queue, increment the size. So going back onto this, first thing you do is you put the data in there, 70. Next thing you do is you increment tail. Next thing you do is you check to make sure you didn't reach the end. That's okay. Then you increment the size. Done, correct? Return. Got that done. Next thing we do, increment 64. Check to make sure it's empty. Size, or it's not full. Size is okay. We put 64 in here. That's of course hex. Increment the tail by 2. Increment the size by 2. Done. Enqueue again next. It's not full. Put 41 in there. Tail is now 3. Size is now 3. It's not at the end. Enqueue 42. We checked to make sure it wasn't full. This becomes 4. This becomes 4. It's getting pretty darn full. Enqueue 43. So tail is incremented by 5 or to 5. Size is 5. It's not reached the end. 5 or enqueue. That's fine. All right. Dequeue. Dequeue, if you remember the code now, says check to make sure it's not empty. If it's empty, there's no need to try and grab something out because it's not there. Grab the data, which would be T, which is what you're going to return. Increment the head. Check to make sure you haven't gone past the end. Increment the size, or decrement the size. So let's go back here. So what we're going to do is we're going to set T is equal to whatever we just read out. It's 70. It was 0, then it's 70. The next thing we do is we said that we would zero this out. Then we're going to increment the head. Don't touch the tail. Decrement the size. Done. So if we were by chance to enqueue, I'm going to do a couple more of these really quick. So we're going to enqueue 30, 31, 32, 33. You could probably all tell these are ASCII characters. Number 1, we're going to check to make sure that this is not full. It's not. So we will put it in this place. The Tail will be incremented. The size will be incremented. We didn't reach the end. Go on, that's done. Enqueue 31, check. Size too big? Nope, it's fine. So we will put it in here. We will increment the tail. We will increment the size. We will make sure it hasn't reached the end. We're in good shape. Next one, 32. We check for the size, it'll still fit, 32. Oops, increment the tail to 8, increment the size to 7. Oh, by the way, 8 is then equal to the maximum size of this array. This is, remember we said Q size was equal to 8. So because it's 8, modulo 8 is 0, this now changes to 0. We're done. Next one, Enqueue 33, the size is 7, it'll still fit. We go back up to this location right here. Oh, we'll put it up here, because that's where tail says it is. That becomes 1, that becomes 8. No need to worry about wraparound because, we've done this. If I were to do this for the next one, 34, first thing it does is it checks the size, it's full. So it doesn't even try to put it in. Now, whatever the program does, that would allow it to be consumed later. You don't have any room in the queue to deal with it. So you would have to, for example, if this were coming in from an RS-232, a UART, you would be in pretty big trouble because you don't have a place to store the character. You might just actually lose the character. All right? Easy enough? If this showed up on a quiz or exam, you would have no problem, right? All right, thank you very much. That is the end of the queuing example video.